Hello, this is Scott from Optics Realm. It's November 2011. Today we're going to talk about field wavelength and lens layouts in Zemax. So the goal is to understand more basic parameters for modeling an optical system. First, I would like to discuss wavelengths. So wavelengths, how do you get to the wavelength setting? It's got this button here, WAV, and it pulls up this dialog box, wavelength data, or you can get it by hitting Control W. And what is it? It's a series of wavelengths specified in microns, and you could enter one wavelength, you can enter 24 wavelengths. You use these check boxes here to specify how many wavelengths you have, as well as the weighting. For optimization, you want less wavelengths because things go quicker, things will ray trace faster. During detailed analysis, you want more wavelengths. You want to ensure you get accurate simulation and you don't get any aliasing. Let's take a look at sample wavelengths. I could hit Control W to get wavelengths. I could hit this wavelength button, or I could go to System and drop down and get wavelengths. Control W shows you here also fields. I'm going to go ahead and hit Control W. I have 9 wavelengths. I tend to do overkill when I'm doing analysis. Let's pick F, D, and C. You hit Select. It updates. F, D, and C equal weights. The primary wavelength is this one. Let's go to the photopic curve, bright. That's your eye in daylight. And it updates the wavelength weightings based on how the eye response is. These numbers are going to affect MTF and a whole host of other things. So here the primary wavelength is 3. We hit OK. It's not going to change that much. Let's look at the bottom here. I just want to show you this. So at this particular, this is a doubly telecentric system, so it's kind of like an afocal. But it's got a very long focal length, 1797.18. Let's go back to the wavelength. Let me change it to wavelength 1. So it's saying the primary wavelength is wavelength 1, 470 nanometers, where it was 555. Let's hit OK, and notice the focal length has changed a little bit. And that's because you're changing at what wavelength you're calculating it at. So it's important to pay attention and pick your right wavelength, preferably either the center wavelength or the one that is weighted the highest. How do you specify field? Field also has this button here, FIE, and it brings up this dialog box here, field data, and you can also get it by hitting Control F. So you've got X and Y, you've got weight, and you've got these vignetting terms, and these weights are used during optimization. I want to talk quickly about nomenclature and field of view. So a lot of people use the term field of view loosely, and field of view just means how big is your field in your imaging system. It could mean an angle for collimated lenses, or it could be the spatial extent on your imaging plane, either your film or your CCD, CMOS imaging. And when you specify it and you get quantitative, you really shouldn't use just straight field of view or FOV. And that leads to redundancy, and it can create a lot of problems with factor of 2. It's much better to say half field of view, HFOV, or full field of view, FFOV. Here's some visible detector formats. This is pulled from Edmund Optics website, and it shows the various formats, 1/4 inch to 1 full inch, and it gives the size in millimeters in X versus Y, as well as the diagonal size. When you model in Zemax, you're entering not the full diagonal, but you're really entering the half field of view. These numbers really are full field of view. Probably should have put full field of view there. So there's 4 methods to specify field, and I'm just going to quickly detail them here and go into a little more detail in the next slides. Angle, and that's this angle. So what I'm doing, this red ray, I'm tracing the chief ray here, and it originates from your object, goes through your entrance pupil, and it lands on your image. So you can specify this angle. You can specify this object height spatially. This is 1 millimeter or 1 inch. And then there's 2 ways to specify image height, either paraxial or real, and that's just specifying the height in the image plane. Let's talk about field in terms of object angle. I've went to Zemax and I've pulled out under their samples. This is a Cook triplet. This is showing, this Cook triplet is optimized for a collimated field. You see the on-axis blue rays, and this is showing a ray trace for plus or minus 20 degrees. Angle is preferred for an infinite conjugate. You can use it for a finite conjugate, and it will just compute the angles, but normally people aren't calibrated to that. Let's talk about field in terms of object height. I've pulled up one of Edmund Optics' large format telecentrics. This is a doubly telecentric lens in object space and image space. We'll be covering telecentricity in other videos later. In this case, I've specified object height. You can see here I've gone from 0 to 30 millimeters. Again, this is half object height. So this is your 0, 15, 20, 25, 30. Likewise, I can specify field in terms of the image height. Okay, so, and I've flipped signs here. I've gone, -7 to -15, and again, it's a factor of 2. This is a half X magnifying telecentric lens. So I'm specifying -7.5 to -15. That is this image over here. You use PARAXIAL when you want fast ray tracing, and you do it for low distortion systems. So for instance, I chose this lens because it's got very low distortion, and this is a grid distortion map here. The grid is where the rays are shot in. The X's are showing where the actual rays fall, and the X's are falling at the intersection showing low distortion. I'll show that here in Zemax in a moment, how to get to that. As opposed to doing the field in terms of image height. So in this case, I've pulled out one of Leichen's wide field of view lenses. This is also a sample that ships with Zemax. And I chose this because it's a 100-degree full field of view, 100-degree input full field of view. When you pull the sample up, it's specified in terms of angle. The field is specified in terms of angle. But I switched this to specify in terms of real image height, 0, 9, and 14 millimeters. And I'm showing you this because it's highly distorted. Typical to large field of view systems, you get very large distortion, and that's shown in this grid distortion map here. Use real ray tracing when you have distortion, and it's going to slow down ray tracing because it's going to have to iterate a little bit. To do layouts, there's two types of layouts. There's regular layouts, LAY, and 3D layouts. This is a 3D layout of a perfect lens with a 30-degree field of view. To modify the settings of the layout, you can hit the settings button, which is up here, or you could do a right click anywhere in the layout, like for instance here or here. And it's going to come up with a whole host of options that you can change. You can change the number of arrays. As well, when you're out of this settings page, you can hit page up, page down, home, and rotate the view. Let's quickly go over vignetting. Now, this is the start of a doubly telecentric layout. This is actually a sneak peek for my Zemax video number 5. In this case, what I'd like to show is this surface that's highlighted red. I've prematurely cut the aperture down to 11 millimeters, and you can see this ray is getting clipped in this layout. If you click this button right here, Set Vignetting, it's going to modify all these parameters here, and I'll show next slide what those are. And it's going to modify this ray, this input ray, such that it gets through the system. That's vignetting. And it's a good idea to usually clear vignetting and set vignetting, because if there's existing vignetting terms in there and you change things, it could bias the output. This is a notional diagram. This is showing your object space. So let's just pretend we have a point object here. We have Y field and X field. This is your notional entrance pupil. And let's say that your notional entrance pupil, and I'm showing a very bad pupil aberrations, or this could come from a tilted and decentered system, but let's say this circle here is your entrance pupil. So Zemax is going to control getting these rays at these peripheries by several factors. You've got VCX and VCY. The C stands for compressed. What it does is it's going to take a ray here that's out at this edge, and it's going to compress it in a little bit, as well as it's going to decenter it, and that's VDX and VDY. This is a Cartesian coordinate system. There's also this rotation angle, VAN, V-A-N. Here's Zemax. Let's talk about, this is this large format telecentric, half X magnification. I've hidden the prescription here. I'm just showing the diameters because I'm going to use this to describe vignetting terms. How do you change what this looks like? You could go settings, and let's say we'll go from surface 8 to the last surface. So that's going to show a portion of the lens. Let me just go ahead and go back to the object plane. For instance, let us suppose this surface right here, which is this surface, let me cut this aperture down. Zemax is setting the aperture, saying it's at 17. Let's say it's at 15. So I could either come to this and hit update or just double click right here. You can see these lenses get clipped. The other thing I want to point out quickly, and I know I'm jumping around here a little bit, is notice right here in the bar there are coordinates, and those are the coordinates on the drawing. So if you want to know where this ray comes to, this is about at 16.3, negative 16.3. And of course we're at 15, you can see this 15 here. So how do you correct this? This is vignetting. And again, it's doing that because it's wanting this ray to get through the center of the aperture stop. I'll hit Control F, hit clear vignetting. I know I don't need to do it because it's already 0, but it's force of habit. Set vignetting, and you can see that it's decentered and it's compressed the pupil. So we'll come back here, I'll double click and hit update, and you can see now that that ray gets through the entire lens. This is object height. Now I'm going to change this. I'm going to do it by a factor of 0.5 because that's the magnification. And we're going to go to paraxial image height. You can see the rays don't change. I double click there. You can see the rays don't change much. And that's because it's got low distortion. So you can get distortion either by field curves, which is this FCD, and you can see it's 0.05%, or you can get a grid distortion analysis, miscellaneous, grid distortion, and you can see there's very little distortion, and the rays the distortion is on top of your nominal paraxial grid. I'll repeat this for the fisheye lens, and you can see how that varies. So this is specifying field in terms of object height or paraxial image height. And just to hammer home, since there's no distortion, I can hit the real ray height, click OK. I'm going to double click and update. So double click, and you can see it doesn't change all that much. As opposed to, here's this wide field of view lens. And I'll go ahead and show you the distortion, analysis, miscellaneous, grid distortion. So what's happening is this grid is your paraxial perfect grid, and these X's show the distortion and how there's a variation in mapping from object space to image space. So for instance, this one's already set up. I've got real image height here, and I've specified out to 14 millimeter half field. And just to prove it to you, here's roughly 14 millimeters, 13.98. And let's change it to paraxial and see what happens. Okay, I'm going to double click. Actually, let me zoom in on this. I'm going to double click, and you're going to see this image height changes. So that is the difference between using real and paraxial. On a system with low distortion, it doesn't matter. On a system with distortion, it makes a big deal. So here's the homework. And before I go into homework number 4, I just want to comment that homework from Zemax tutorial 1 and 2 were identical. Sorry for the confusion. We're starting slow on the homework. It's going to pick up. This homework, again, is identical to homework 1 and 2. And all I'm asking you to do right here is add your diagonal, 9 millimeter diagonal sensor. It's your half-inch CCD. This is at the other side of the tube lens. So depending upon how you set your system up, whether your objective was first in your microscope or your tube lens was first in your microscope, you're going to need to set your fields accordingly. And once you've done this, what is the size of the object field? Your detector plane is 9. What your subject that you're blowing up in your microscope, what is the size of the field? And it's easy to calculate based on the magnification of the telescope, but I'd like you to verify it in Zemax. There's a reference for microscopy, the optical design of microscopes by G. Seward. There's optical systems in there, and he's got the actual prescriptions in the appendix. This is Scott from Optics Realm. This was Zemax number 4. If you liked this video, please hit like at the bottom and subscribe to my YouTube channel. Thank you, and thanks for tuning in.